Okay, let's get started. Good morning, everyone. Welcome to the first press conference of the 221st AAS meeting here in Long Beach, California. I'm Rick Feinberg. I'm the AAS press officer, and it's my privilege to welcome you here this morning to a briefing about exoplanets. A few quick announcements before we get started. I wanted to point out that throughout the week I'll be assisted by I'll be assisted by my deputy press officers, Inga Heyer in the back, and Larry Marshall over here, who I can't see because he's standing right under a bright light. They'll be sharing the briefing MC duties with me throughout the week, and they'll be with me in the press room as well. Standard reminder, everybody make sure you silence your cell phones, pagers, etc. For the journalists who are here, the press tour there's a sign-up sheet for the press tour on the bulletin board in the press office. We have a tour to Space Park in Redondo Beach, which is right next to LAX, Friday morning to see some JWST hardware, James Webb Space Telescope hardware, and to hear about the status of the program from some of the program scientists and engineers and managers. We will be having a press dinner on Wednesday evening. I haven't got those details fully figured out yet. There will be a sign-up sheet in the press room a little bit later. All right, those of you who've been here before know how this works. We have our speakers present in order from left to right, and then at the end of the presentations, we open it up for Q&A. So you'll have to hold your questions for the speakers until the end. We are webcasting the session, although we are having some technical difficulties at the moment, so the webcast hasn't actually begun, but we're hoping that it will have begun by the time we get into things, and there will be questions coming from the online audience too. Well, if you've looked at the press program, you've noticed that 30% of it is devoted to exoplanets. Exoplanets are the new hot topic in astronomy, or at least one of the hottest. Some of the exoplanets are really among the hottest things we know too. And it's amazing how far we've come. Everybody in this room remembers the time when we didn't know if there were planets around other stars. And now we know that there are planets around most stars, lots of planets. And they're very different than what we're familiar with in our own solar system. And so we have, over the course of the meeting, 3 different briefings on a wide variety of exoplanets, not just the planets, but the stars they're orbiting, not just fully formed planets, but planets that are still forming, planets that have evolved in star systems that have died. So it's really quite a potpourri, and will be quite enlightening. Today we're going to be hearing from 5 speakers, several of whom are affiliated with the Kepler project. This is NASA's space telescope that's staring at a spot in the sky looking for exoplanet transits and is producing by far the largest number of exoplanet candidates that are out there. So we'll hear a number of results from that team. So from left to right, the speakers are Christopher Burke from the SETI Institute, who will be speaking about 2 years of precision photometry with Kepler. Francois Fresson from the Harvard-Smithsonian Center for Astrophysics, who will be speaking about the frequency of Earth-sized planets. Joe Carson from the College of Charleston, speaking on a newly resolved disk in a search for exoplanets around certain types of stars. Then Nathan Cabe from Queen's University in Canada, who will be speaking about planetary system disruption in wide binary stars. And finally, I've asked John Johnson to come. He's one of our prize winners giving a plenary at this meeting. John has presented before. He's very involved in the theoretical understanding of exoplanet systems. That's the other thing I wanted to mention, is that it's not just the discoveries of these systems and the characterization where we're seeing so much advance, but also in the understanding of how we get planets and what happens to the planetary systems as time goes on. So with that, I'll turn it over to Chris. Are you using this laptop? Okay, well, let's see if we can get your presentation up. And I may need some help, Damon. Which one is it?
It's this one here.
There we go. All right. So where's my play button?
I think if you go to view.
Oh, it came out.
I got it.
All right, very good.
Great.
Thanks a lot.
Excellent. Thank you. All right, well, thank you. On behalf of the Kepler project, I want to thank the AAS for organizing this event. Today, the Kepler project is announcing 461 new Kepler planet candidates. For For those of you who are unfamiliar with Kepler in the audience, Kepler is a NASA space mission which is managed by NASA Ames, and it's finding these planets in stars outside the solar system using the transit technique. The main goal of Kepler is to find planets in the habitable zone and characterize the population of these kinds of Earth-sized planets. So as a stepping stone towards this goal, we've announcing 461 new planets, and what I'm going to do is take a little bit step backwards in time to 2 years ago to put these new results into context. So here's the planet candidate sample that we had 2 years ago. We had around 12,000 planet candidate objects. Here I'm showing orbital period versus planet size. A year later, we added a significant number of new objects. Definitely, we saw the trend of huge numbers of very small planets, like super Earth, twice the size of Earth and smaller. And now, with this new data set, we've analyzed 22 months' worth of Kepler data, and we're adding 461 new objects. This brings the total count of planet candidates up to 2,740 found by Kepler. Now, in this figure, Kepler is most interested in the things on the long orbital periods and the small planet sizes. Those are the things in the lower right corner here. As we get more data, we'll get more sensitivity towards those parameters. So to summarize, we have 461 new planet candidates. In the rest of the talk, I want to demonstrate these three main points. What we see in this new sample of object is the growth of new objects is predominantly in the super Earth to Earth-size objects. We really increase the number of those objects that are now planet candidates with Kepler. Second of all, we are continuing the trend of finding these planets in multiple planet systems. These are stars that have more than one planet in them. These systems are extremely exciting because you can do very interesting astrophysics. You can learn about planet formation when you study the dynamical interactions between these planets in these multiple planet systems. And finally, we'll focus on these habitable zone planets. The habitable zone is where liquid water can hopefully sustain life-bearing organisms, and so we're trying to find these things. You need very specific conditions to have liquid water. You can't have your planet too close to your star to be too hot, and it can't be too far away for the planet conditions to be too cold to support liquid water. So we're trying to find these planets in this very specific zone, this habitable zone. So to demonstrate the first point, here now is a breakdown of the cumulative total planet candidates found by Kepler. The histograms are bins of planet size. The leftmost bin is one of the more interesting ones. We now have 351 Earth size, which is 1.2 Earth radii and below. Now the percentage there is the percentage increase from our sample from a year ago. So you can see we grew the number of Earth-sized objects by 43% from a year ago. This is expected as the data from Kepler grows in size. We're able to be more sensitive to these very much smaller signals. Again, we saw additional increases in the super Earth size. These are things that are twice the size of Earth and smaller. So here now I'm demonstrating the multiple planet systems that we have. The different rows are the number of planets that Kepler has observed in these systems. Starting at the top are the planet systems with only one planet, down to 2, 3, 4, 5, and 6. The column on the left is the planet sample candidate from a year ago. And now in 2013, with this cumulative result, are the planet candidate totals in these multiple planet systems. So we've added systems that now have 5 observed planets in them, is up to 11. We still have only a single 6-planet system right now, but growths across all of these categories with this new catalog. And the final point I'd like to illustrate are these new habitable zone systems. The new systems we're announcing are these points, the yellow points here. And in this figure, we're interested in the things down in the lower left corner of this diagram. This green strip there is this habitable zone that has a very specific conditions that can possibly have liquid water. So what I'm going to do is zoom in on this habitable zone so we can look at these most interesting candidates. Here, our new candidates are marked in yellow. And what I want to bring attention to is, in addition to the large number of yellow objects smaller than Neptune, I want to bring your attention to just 4 of these new habitable zone candidates found by Kepler. These all 4 have estimated radii to be less than twice the size of Earth. In particular, one of these is around a solar-like star. The other three are around stars that are much cooler than the sun. But we're very interested in finding planets around stars like our sun, like we live around here in our solar system. This one is a radius of 1.5 Earth radii estimate, has an orbital period of 242 days around a solar-type star. So that one in particular is very interesting. So to summarize, we're announcing today 461 new planet candidates. The cumulative total now with Kepler is 2,740 across all the different planet candidate samples we've announced. The largest population increases are in the small planets, the Earth size and super Earth size. We really increased the fractional numbers of those. The next bullet talks about the multiple planet candidates. We've increased just the number of multiple systems, but we've also continued the trend that multiple planet systems are very common. If you're a planet that Kepler has observed, you're 43% likely chance to have another planet in the same system. That's been observed by Kepler. Finally, we want to focus on these 4 new candidates in the habitable zone that are less than twice the size of Earth. And one of these is particularly interesting because it orbits a sun like our star. The planet candidate table for these that I've talked about today are available at the NASA Extrasolar Planet Archive at the URL listed there. Thank you.
Hello, I'm François Fresson. I work at the Harvard-Smithsonian Center for Astrophysics, and I want to report on a very exciting result we got with a collaboration with other people working for the Kepler mission at the NASA Ames Research Center. And we've been able to work on the candidate catalog and find what is the underlying population of planets. And the headline of our work is we found that at least 1 in 6 stars has an Earth-sized planet. So we worked on the February 2012 catalog, so the previous catalog, and we know that the list of Kepler candidates contains most of the knowledge about exoplanets. And in fact, we still have difficulties to digest it, this paradigm shift that occurred when the candidate catalogs were released. And another reason that they're tough to digest is because there's a few issues if you want to extract what is a chance for a star to hold a planetary system just from these histograms. First, it's the fact that the catalog is not complete. For every planet that Kepler sees transiting, there's dozens that are not transiting because they are not well aligned with the observer. And also, even if Kepler is extremely accurate, he's not able to find out all transiting systems, especially the smaller planets transiting the larger stars. And the second issue that is also difficult to disentangle is the fact that the catalog is not pure. Despite all the efforts that are led by the vetting procedures that leads to the candidate catalogs, there are false positives among the small dots that constitute the histograms. There are some of those that are not due to planets transiting their host stars. So in order to correct for the incompleteness, what we do is we've been using the actual detection level of a list of more than 2,000 candidates to find out what is the actual detection recovery rate of Kepler. And to correct for the impurity, we had to tackle the issue of these false positives. It's well known that an observed periodic transit signal could be due to a transiting planet or any kind of astrophysical configurations of 2 eclipsing objects, eclipsing each other, in the same pixels as the stars we're observing. And what we've been doing is we've been doing a simulation of the Kepler survey, focusing on all these false positives, and trying to take into account all configurations we can think of. And we found out that altogether, these configurations could only account for 9.5% of the huge number of Kepler candidates. All the rest, even if it's very difficult to check which ones, are bona fide planets. And here is our most important results. This is the occurrence of planets, so the fraction of stars that have at least one planet. The numbers for the large Neptunes and the gas giants on the right were fairly known already, but there's a dramatic increase in the occurrence of planets when you check for the small Neptunes column. And we were able to provide what could be considered as the first robust estimate of the occurrence of super-Earths and Earth-sized planets, the most important result of this presentation. So we were only able to provide it for the short periods, simply because there's not enough candidates at longer orbital periods. But we can say that 1 in 6 stars has an Earth-sized planet within the orbit of Mercury. So why can't we provide an estimate in the habitable zone? Where do we fail? We don't. It's simply nature is such that in order to catch several transits, like 3, 4, 5 transits of an Earth analog orbiting in 365 days, you have to wait for 1 more year to get another transit. So it's simply too early to call. We only have 30% of the whole Kepler data in. Kepler is still observing. We'll be able to make a statement, but it's right now too early to call. But there's another very important result that we get along these lines. So 70% stars have an Earth-sized planet only within 85 days, but if we add the larger planets, and if we go up to longer periods for which we can make estimates, we already know that 70% of stars have a planet of any kind. And we know it's not complete for the Earth and super-Earth, but 70%. And if you make very reasonable extrapolations on the current Kepler observations and also results from other detection techniques, it's very easy to claim something like that is very close to 90%. So think about it. Almost all sun-like stars have a planetary system. If you randomly travel to a star, it will have a planet. We can't say if it will be welcoming, but it will have a planet. But you're going to tell me, we've only been studying the previous candidate catalog. So what about the ones that has just been released and I'm kind of discovering at the same time as you do? So I've only been able to run very preliminary tests. And in fact, if I apply the occurrence rate I determined, and if I assume that the observations lasted 22 months instead of 16, I was expecting to find only 260 new candidates. But Chris just reported that there were 460. So what's wrong? Are the numbers I presented wrong? No, it's the model of the detection of Kepler that improved. So the numbers still hold, and Kepler is doing better at finding smaller objects. And another very interesting side results we had is it was previously thought that small planets were way more common orbiting small stars. And what we found out is the fact that the occurrence of small planets orbiting large stars was underestimated. And so right now the two numbers are quite close from each other. And in fact, the results of Kepler can be explained with planets equally common orbiting the different stellar types. And I think my main headlines are very easy to remember. First of all, you have to look down. So if you look down, you'll see that we're standing on a planet, and these kind of rocky objects are everywhere. And the second headline is, if you look up on a starry night, each star you're looking at, almost each one of them has a planetary system. Thank you very much.
Hello, I'm Joe Carson from the College of Charleston, and I'm going to be talking about direct imaging observations, looking for planets and more importantly for this one, in disks. And this talk focuses on the imaging discovery of the debris disk around HIP 79977, which is shown in this infrared image that you're seeing edge on. I'm giving this talk on behalf of the Subaru Seeds debris disk team, and Christian Thalman at University of Amsterdam is the lead author of this investigation. which appears today on the Astro PH preprint server. This is interesting. This is one of only a handful of debris disks that's ever been resolved around a star. These debris disks are these large wheels of dust and material that we often see, particularly around young stars. And this is analogous to our own Kuiper belt in our own solar system. But this system that we're seeing here is much more massive. So we observe this as extending out about 10 times further than our own solar system's Kuiper belt, containing far more material. One thing that's also quite interesting that you can see in the lower panel of the frame at the bottom is that in image processing, if we remove the light from the debris disk, we do see what we have now is an unconfirmed point-like source that we see relatively close to the star. And we're following this up with more observations, but that point source represents a candidate exoplanet, or if not an exoplanet, probably a clump of dust, a localized clump of dust that's within this debris disk, and is right in the heart of the dusty material of the disk as well. This discovery was made as part of the International Subaru Seed Survey. This is a survey using the Japanese Subaru telescope. The survey is headquartered at National Astronomical Observatory in Japan and led by Motohide Tamura. And we have a relatively large, rich international team of researchers from around the world. And as I mentioned, for this investigation, Christian Tallman is the principal investigator for this particular investigation. And this research is supported by the U.S. National Science Foundation. The discovery was made using the Subaru telescope and also using the AO-188 adaptive optics system, which we use to remove the distorting, blurring effects of the Earth's atmosphere. And we also use the Haichao science camera, which is a specialized science camera, particularly for very high resolution, very high contrast imaging. If you were to look at a raw snapshot of one of these images, the light in the image is completely overwhelmed by the glare of the host star. We take in advantage of an angular differential imaging technique where the field of view is rotating during our images, and we can use that technique to remove the glare from the host star in image processing in order to unveil the feature of the debris disk and also this candidate extrasolar planet. Once we made the discovery that's shown on that left panel, we followed it up with differential polarization imaging. And here we can look at how the incident starlight that is scattering off of these particles is polarized, and we can compare it, for example, to the material that we see in our own solar system as light scatters off of it. And the map of that polarization image is shown in that lower right panel. The system itself it's quite interesting. It's about twice the size of our own sun, which might help explain why it has more material around it, or much more than we see in our own Kuiper belt. When we looked at the degree of polarization from this scattered light, we find that the degree of polarization is very similar to how light scatters off cometary dust that we see in our own solar system. And we know that our Kuiper belt is one of the residencies of comets. And I think one thing that's also interesting about this system or about these systems in general, is that we know that the debris disk or this dust material that we see, we believe to be produced by collisions of planetesimals closer into the star. And this is the material that's probably being blown out from them. So what we're largely seeing here is, we're seeing a story of planet formation, or we're seeing an important step in planet formation that's a connection or a chain link between these, the planet formation that we think might be going on inwards, especially with some of these planetary collisions, this cascade of planetary collisions, and going on to the full, more mature exoplanet systems that we see today with